Hey guys, welcome back. All right, so I was clunking around. I figured I'd release a few more videos, but I got stuck in a few places, so I didn't want to release those. So in this case, I'm just going to walk you through what I did. That way, it's a lot more straightforward, and you don't have to. I don't have to waste your time, and you don't have to waste your time watching me clunk around. So anyway, we did implement the setQ functions, and we were able to replace our hard coding of variables. So we don't have to do this anymore, but instead we do have to, now that these aren't hard coded, we would have to use the setQ function to actually get those back in. So that part's handled. The other thing that I did is I rearranged what we were doing with the multiplication and addition functions. Before, these were if-else, and I wanted to just break these up into more try-catch type things again. And those aren't fully tested, but I still think it's a better structure, just to try to do one thing, and then if it fails, try to do another thing, and so on. So those are restructured, and if they don't work, I mean, we can always revert back. It's not the end of the world. It just seemed like it was a better structure to try one and then waterfall to the next, to the next, to the next thing. The other thing that I didn't want to deal with inside of a math function was dealing with strings. So I'm only trying to deal with strings as far as getting variables back. Otherwise, I'm sending back a blank string, and then if that blank string is, sorry, I'm setting this to a blank string. If the string is blank, then it's just going to return error because it realized that, hey, I have no valid variable that's set to a string, whatever. So just return error because you're not a numeric value. So that's what we did with addition and multiplication functions. Now, well, same repeat. Yep, did the same thing, except for it's plus equals instead of times equals. Okay, difference being, in these cases where plus equals and so on. The other thing we added was, I added three more things. I completed the basic math operations. So plus, multiply, we did minus or subtraction, and where are we? Division operations, which proved to be a little bit more tricky than just for basics. They ended up being twice as long as the, I don't know if you can see that, twice as long as the multiplication and addition. So we just ran through a try-catch first because we needed to set the sum to the first value that was passed in, but we still needed to try the same operate. Are you an integer, double, so on, or are we going to throw back an error of some sort? And then, it just keeps going. So again, probably not perfect, but we did it. So we have division now. Whoops, messed that up. Control Z. Okay, and then up above these two, we have also the modulus function. So that should pretty much round out what language or programming language would consider basic mathematical function. And that one was unique in the sense of we went through a very particular process to figure out what that would mean. So I fumbled around again with that and didn't want to waste your time. So I just kept it. Basically, I'm going to keep it off camera or off screen, and we're just going to walk through it now that I've completed it, so we don't have to stumble through it. Okay, so that being said, let's go ahead and look at the subtraction function. Subtraction function basically sets, like I said, the first value, the first parameter, I should say. Remember, the first value is the function because it's function first. So the second is the parameter, and anything thereafter is the parameter. So now we have the first value, and if it is a valid numeric, then it basically goes in and becomes the sum. Because when we're subtracting or we're dividing, we always want that first value. But to do that, so I tried that first, and then we iterate over all of the rest of them. So we start at basically the second index or the third value, right, for script parts, and then so from there on after it's going to take the sum, because it will already have something in it, and it will pull it out iteratively if it's able to. Otherwise, it will return an error. So that is basically what we did with that. And then if for some reason we run into an error up front, we don't even waste our time here. We just say go to, and then I made a little label here to say go to this end early label, and don't even try this for loop, and then dump the error and come back and do your thing. Okay, so same thing for division. We just set it the same way, just because it's not as straightforward as the addition. Primarily because we can't subtract from 0. If we subtract from 0, the first number becomes negative, right? And then division is somewhat the same. We can't divide by 0. Dividing by 0 is an erroneous, at least computer operation, and very difficult human operation. And I guess while we're there, I might as well describe why there's an error. It's a good tidbit to know, I guess. You might not like to know this, but I'm going to tell you because I think it's cool to know. All right, so the reason there's an error when we divide by 0. If we did 1 divided by 10, oops, sorry, we'll do that like this. That decimal value would be 0.1, right? And then so on. So we say if we did 1 divided by 100, that becomes 0.01, and then so on. We add a 0 here, we add a 0 here. And we keep doing that, and we keep doing that. And basically what we're saying is the bigger this denominator gets, the closer to 0 this becomes. But because 0 isn't really a thing, this denominator basically becomes an infinity, which is impossible to calculate because it just keeps going. So instead of 1 divided by 0, it's basically saying infinity. So if you can imagine that, that's what's going on. That's why this 1 could never be trapped no matter how far it gets out to the right. And worth mentioning, I thought. There's an easy enough explanation. There you go. That's my version of why. Now, someone else might have a different argument. That's fine. I'm not really trying to argue it, but that's what makes sense to me. I figured it's worth sharing. Okay, anyway. Done with that. So, we've got the mathematical operations working. Now, let's go and look at the setQ. setQ is what we were really trying to do so we didn't have to hard code values. The structure is very similar to what you've seen already because our parsing is very similar to what you've seen already because it's going through the same basic steps. So what we did is we created a dynamic because remember in our storage, I'm going to just scoot up here. So in our storage dictionary, user vars, it takes a string and it stores a dynamic variable. So that dynamic variable could be of all sorts of types, right? And for now, we did it like this. So we said if you're a numeric integer, parse it as an integer and put that into the storage value. If you're not, catch that, right? Because that would fail as us trying to do it. Catch that and then try to do that as a double value. If you fail in that, catch that, and we're going to catch it, and we're going to just pass it back as a string. And then we're going to add that back to the user vars dictionary with the .add C# method. We're going to grab the script part 1, right? So we're limiting it to 2 parameters. The first one being the the variable name, and then the second parameter being passed would be the parameter value, whatever type it may be, as long as it's one of these 3. And then we return it back to script, and we replace it with nothing because it's like a void function, right? We're basically returning nothing. We're not returning a value. We're just setting a variable. So, and then we go through, execute the loop like normal, and then we replace what we were trying to evaluate in our script, just like we have the whole time. So that function was fairly, or that parsing, right, of this function was fairly straightforward, fairly easy. So let me cover the modulus. Let's go back and cover the modulus, what was happening, what I was stumbling with, and then we'll just start the code and we'll run through and we'll test all of these things, and then we'll be done. So I wanted to make sure that I was able to cast everything as a double, even if it was an integer. And the reason for that is because the modulus function is all about trying to get a remainder of division. There's a problem with that. The problem with that is, and there might still be some old code up here. There is. Okay, so the problem with that is if I divide an integer by an integer, it returns an integer. But if I divide an integer by a double, it returns the double, right? Because there is actual extra decimal information out here. So there's a reason that I'm casting that first evaluation to a double, and then I'm subtracting it from the integer operation so that I could get the remainder, which is this part. And then I'm taking that part and I'm multiplying it back times the denominator of the division operation. And then what I did is I was experimenting with some of the, so again, this is not a perfect implementation. I'm multiplying it back and getting a rounding out at 15. Well, 15 is kind of probably a max for a max range for a double. So then I just reduced it to 10. Remember, the further we get away from the decimal point, the more this becomes closer, right? Anything before it becomes closer to 0 or whatever. The smaller that number gets, the closer it is to 0. But because of the rounding at the very, very end, right, I started to jumble the numbers for some reason. This is just the way it happened. Maybe if I turned that to 14, it would have been okay, but I just chose 10. 10 is a really accurate, right, display of that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We rounded it way out there. For anything practical that most of us would be dealing with, and no, I'm not talking about rocket surgery, right? I mean, you're going to send rocket to a moon. Those numbers need to be extremely accurate, way out, way out, way out there, because you're sending things really, really, really far away. So your margin of error is really, really small. So for us, though, even 10 digits, that for most things, that's okay. Think about it, measuring something in inches, right? Even in manufacturing or machining, we talk about things in the thousandths or the 10,000ths, right? Around these two, and that's just 4 digits. We got a whole nother digit to be 5, and then we got double that. So for practical things, those numbers are fairly accurate. So we just rounded to 10, and that gave us basically the modulus function. And I tested it with a few different things. We divided, we got the remainder, and we just tested it. We made sure that what we did made sense, and we have a valid modulus function. Okay, anyway, so let's go through that. How did I implement what we fumbled through then in the C# interactive? Well, we did the double parse, so we got a numerator and we got a denominator by parsing the same thing. And again, we limited it to 2 parameters, similar to the setq. We limited this function to 2 parameters only, so it didn't get confusing. It's not iterative like any of the other math operations we've done to date. Okay, and then we implemented the double version, right? Double, so that's numerator, denominator. We divided those, and then we subtracted just like we did here, and then we cast the division of this into an integer, right? Just like this. And then we multiplied by the denominator, which is there. So this is there, and it is a double, right? See the dot 0, right? It's a double. And then we considered the rounding to 10 decimal places as a built-in constant. So this isn't something you're going to change through script. Okay, but that is the function. So, and then of course, if it runs into an error, like it couldn't parse this thing as a double, it's going to set an error, right? Just similar to what we've seen before. It's going to set that to a blank string, and if it's a blank string, it's going to replace it with error, and then it's going to replace the thing that we're evaluating, the total function body of just that modulus call. It's going to replace that with error, and then it's going to keep propagating an error, and that's what we'll see on the screen. So that is my walkthrough of the code. I know it was a lot, but it was a lot of very similar things to what you've already seen. So let's walk through it. I'm going to save that. Let's go ahead and start it. And we will have to initialize our variable. So let's make sure that works first. Set q a to 10. Now I hit enter. Now to check the variable, we can multiply it by 1, right? So times 1 and a. Boom, 10. Now what will fail? Well, this will fail, and it will fail miserably, I believe. Yep, it says error. So we handled the error. It didn't crash. It was crashing on me, so I knew I had to do some basic error handling because it couldn't parse B to anything, remember? So because it couldn't parse B, it threw the blank string, and the blank string said, oh, if your blank string on the sum, replace that with error, and then replace that script thing with error and move on. So it kept propagating that error until it couldn't do anything with it. So, all right, now we can set QB to be 20. And now if we tested that, it's good. Okay, so, and then we can set QC to 30, and we can, in the same line of code, because remember it ends by the parenthesis caps. So set QD to 40. And of course it'll evaluate D first, because we know how it parses all the way to the end first and then backwards. But doesn't matter, they both get evaluated until it can evaluate. So now we can check C and D, right? So times C and D, and we know what that is. That should be 1200, right? And it is. Okay, and then we can just test our function. So our function we tested before, we know that should be 1400. So that should all work the same. Times C and D. Cool, it's 1400. That's what it spit out. Right there. All right, now let's try some of the more trickier operations, right? So let's see, can we still, so because I modified the addition and multiplication, as well as we added the subtraction and division operations, and we added the modulus operations, we need to test all of those, make sure that they work at least to a basic level. So let's try that. So we're going to say times 1 and 2 and 3 and 4 and 5, right? We need to know that we know it works on 2 operations because we just did that, these 2 and then these 2, right? So we're going to get rid of that, and then we're just going to say times 1 and 2 and 3 and 4 and 5 and test it. So what would that be? 1 times 2 is 2, times 3 is 6, times 4 is 24, times 5 is what, 120 or something like that? 120, there we go, it's close. So we know that works. Let's do the add the same way. So 1 and 2 and 3 and 4 and 5. So 2 and 1 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. All right, 15, so we know that works. And then let's talk about minus, I guess. So we're going to subtract from, let's say 50. So we're going to start with 50, right? 50 is the first thing we're going to subtract from. So 50 minus 25, and we know that that should be 25. Okay, we subtracted it out. And but if we said 25, again, we know that that is basically 50 minus 25, which is 25, minus 25, which is 0. So 0, and good, that worked. And then if we just said we want to minus 5 more from that, we know we should get a negative 5. And we do. So the other thing I didn't try this in the past when I was fumbling through stuff, is I want to try to subtract from negative numbers. So let's say minus 50, we're going to subtract out from minus 50, we're going to subtract out 25. And we get a minus 75 because it took 50 and it says, okay, I'm going to take 25 more positive things away from you, which is right. It goes to the minus 70. So that works. Now, does that work if I put a minus 25? I'm going to subtract out from this negative number negative values, which will go towards the positive, so it should go back to minus 50. And it does. Okay, so that works. And good. Things are just working the way I expect them. Hopefully you expected those same things. Okay, and then what else? We need to test divide. So divide, we're going to divide 10 by 2, and then we're also going to divide that by, let's see, by 2 again. And I want to show you something that I'm concerned with here. And again, it comes back to, well, here you see it. So it says 2. That's not true. 10 divided by 2 is 5. Divided by 2 is 2.5. Because 2.5 plus 2.5 is 5. So if we did this, though, is true. So remember, if we pass in only integers, integers will reproduce an integer when it comes to the math operations. If it's a double, if it can go as a double, then everything is subject to the double operation, right? Because if this one was a 2.0, then the result would be a 5.0. Now, it might still say 5 only, so let's test that. Let me make sure I'm not lying to you. 2.0, and we're just going to say, is that 5.0? No, it says 5. But if we divided that by a integer 2, will it still be subject to the 5.0 stored double or whatever? And it would be, because there is a double in there. In that operation, it will continue to override. The safe thing is just do everything in double. So it's in our case, right? In our case, just put everything in a double format, meaning just add a decimal place and a 0, and everything will be good. Okay, anyway, that is those functions. Now let's test our modulus. So we know that 5 divided by 2, so we could say, whoops, we got a function first, 5 and 2, right? What is it? So we know 2 goes into 5 times 2 times. And then what's left over? Well, what's left over is 1/2, right? 0.5 or whatever. So 0.5 times 2, right, because we multiplied the remainder times the denominator, which is that 2 right there, and 0.5 times 2 is half of 2, so it's 1. So we should have 1 in it, and that's correct. And remember, this one isn't quite as touchy like the division is, because we forced a cast inside of our modulus function to actually do a double. We cast it specifically, explicitly, to be both numerator and denominator on the modulus to be double. Okay, so anyway, all of those work. The set Q works, right? Because we still have, we did our set Qs up here, right? Correct. Did we? Yep, we set Q, where did I do? Oh, yeah, A to 10. Where did we do B? B was an error there. We set QB to 20, and then we did, what did we do? We did C and D somewhere. Yes, we did, right there. C and D, we set those, and then we did all of our other operations. So that being said, can we set Q? Because this would really be our last test in this case for what's programmed today. Is can we set Q a variable? So we have A already. We need to test that too. I can't remember what I did in code. So if it exists, will it replace it? We know A is 10 right now. Let's just set it to 50. Yeah, it failed. It says, okay, can't do that. Why? Because I can't add you because you already exist, right? So set Q. We needed to check for existence first before we did any of this. One last thing that, of course, I didn't think of until it was time to do it. But let's say that we're just going to do that now. It wouldn't be very difficult. So we would say if, right, in every one of these cases, if, no, not there, we would do it here, way down here. We would say if script parts of 1, right, if the user vars dot contains key of that is equal to false, then we can go ahead and do that part. Otherwise, else, we should be able to say that user vars, let's copy it from here, user vars of script parts equals storage val. And that should now work. So that should have been an easy enough fix. So let's try that again. All right, so we're going to set Q A to 10, right? That's what we had originally. And then we want to try to set Q A to 50. And that worked, hopefully, seemed like it worked, times 1 and A. And we should get 50 back. And we do. Okay. I am satisfied with that. Now, the one last thing I was really trying to get to was, can we set, now that we know we can replace a variable, I'm going to set QA to a mathematical function, right? So I'm going to set it to plus, well, hold on, we need to set all of our variables back. Set Q A to 10, set Q B to 20, set Q C to 30, and set Q D to 40. Hit enter. Those are all set. Now let's go ahead and type in, or I'm just going to copy paste if I can. Control C, Control V, enter. Right, so we still have 1400. Can we set QA to that formula? Well, we know that formula basically produced 1400, right? So I'm going to say times A and 1. Well, it should be 1400, and it is. So A's value is the value of that function, or the return value, I should say, of this function being executed. So I wanted you to see that, because that is where the power of Lisp really comes in, is you can temporarily set variables to all sorts of cool function combinations and use those values over and over and over and over, and we know that what gets returned out of those functions is a value, and we know that we can set variables to values. So you needed to see that. For scripting language sake, we need to know that we can store values, and in this case it was just all part of the tokenizing, or parsing and tokenizing, and evaluation steps out of the expression trees. And it just works. It works, and it's very similar no matter what we do. It's very similar on how we parse it, very similar on how we reason about it. And then the next step is, I believe, the next step that I really need to chase is hitting what I showed you guys in the preview, which is creating that defun function. Hopefully you see that these things are very powerful. And then I want to do something a little bit more, which I did with setQ. I mean, I did something a little bit more than just the mathematical values. setQ breaks away from that mold. It says I'm actually running a function, right? I'm doing something by name, not so much by symbol of plus or minus or divide or whatever. But defun will actually allow you as a user to create a custom function name. So you can have something that says my funny function and have it do some crazy thing that you need it to do, and then, right, you can keep building other functions that leverage the previous function that you wrote. So anyway, I wanted you to understand that, and we need to reason about how to maybe start some of those processes on the C# side as well. And anyway, that's where we're heading next. We're going to also probably deal with another data type other than just list other than just the doubles or integers or strings. We're probably also going to, at least in this case for Lisp's sake, the power of Lisp really shows up when it deals with lists of things. But we have a C# type of list, so again, I think that's something worthy of approaching. That list can store, at least in our case, I think it's wise to keep it limited. That list can store integers and doubles and strings. So it'll just be a list of dynamic type inside of C#. But as far as Lisp is concerned, it is a list of valid values that we use. At least Lisp as we've defined it so far. So anyway, I'm calling it good. I'm putting the marker in the sand for now. For this session, I should say. It's already gone pretty long. So we're just going to ask you to subscribe before we let you go. Ask you to subscribe if there's something you missed or something I missed or somewhere in between where you couldn't make sense of something, leave it in the comments below. I will try my best to respond to those, and we'll pick you up on the next one. All right, take care.